Hello, everyone. In this presentation, we will discuss the mathematical description of the building blocks of quantum computers. The building block of quantum computing hardware is the quantum bit, more briefly called a qubit. It's a simple quantum system with two possible states. However, unlike a classical bit that can only take two values, 0 or 1, qubits can actually be in one state or the other, or even be in a linear combination of both. This comes from the inherent randomness in quantum systems, so that except in special cases, we never know exactly what the quantum state is. In the best case scenario, we know the possible states it can be in with their associated probabilities. So how can we mathematically describe this inherently random state, which we can think of as a quantum coin? We take inspiration from vectors. Here we have a vector v written in terms of its x and y components, with the coefficients a and b giving the weight of each component. So we write our quantum coin state in an analogous way as follows. On the left-hand side of the equation, the symbol with the left vertical line and right bracket is called a ket. Since between these two there's a phi, we read what's on the left-hand side of the equation ket phi. It's actually common to use ket phi as well as ket psi to represent the quantum state in quantum mechanics. On the right-hand side of the equation, we have the two kets corresponding to the two possible states of the quantum coin. Ket h corresponds to heads, and ket t corresponds to tails. Associated with each outcome are the probability amplitudes alpha and beta. The probability of obtaining heads is the absolute value squared of alpha, and that of tails is the absolute value squared of beta. So it makes sense that they add up to 1, since that's the value for the total probability. The matrix representation of a ket is a column matrix or a column vector. So ket h is given by this column matrix, and ket t by this one. Notice that they're orthogonal, which is great because they represent mutually exclusive outcomes. This, of course, implies that the column vector representing ket phi is this one. How do we know when two kets are orthogonal or not? Well, we need to take the Hermitian adjoint of one of them and then calculate the inner product, which is similar to the dot product. So when you get 0, you know it's orthogonal. This is how the Hermitian adjoint of ket phi is represented. Notice the dagger at the top. That's actually the bra symbol here, bra phi. The naming comes from the fact that if you put the bra of a state to the left of the ket of a state, you get a bra ket. In matrix language, a bra is a row vector obtained by transposing its corresponding ket and taking the complex conjugate of its elements. In quantum mechanics, since our aim is computational, the states of the qubit are not labeled by heads and tails, but by 0 and 1, just like bits, in keeping with our computer science goals. That's why the general state of a qubit is often represented this way. How would two qubits be represented? Well, the vector space needs to be expanded to accommodate two qubits, so we have to take the tensor product of the spaces, as you can see here. The first ket corresponds to the first qubit and the second one to the second qubit in all the terms in the sum. To simplify writing, the tensor product symbol is often dropped, so the state is represented like this. Now, I want you to work out this representation for 3 and 4 qubits. Guess what it is for n qubits? Then think about what the combination of zeros and ones inside the kets represent. Until next time.